Hi, and welcome to another exciting edition of CG Programming. My name is Nate Nessler, and this is Hyperactive Studios. Now, before we showed how to go about doing the light models, and what I have right here is a Vertex Lambert shader. And I got a couple things going on here. Besides the ambient light and the ambient color and ambient diffuse, this ambient light's actually pointing to our might be a better name to call it ambient shadow instead of ambient light. Let me change that real quick because I prefer ambient shadow for artist interface. So this is going to make more sense to them what it is doing here. I just need to do a save all real quick and just rebuild real quick. Okay, so it says ambient shadow now. And I think this is a good name for it, honestly, because if I go in here and I start manipulating this, check it out. You see the black areas here as it falls off into shadow? Well, I'm going to pull this up here, if I can get a hold of it. And you can see the result of that. Cool. The other thing that we can do here is the ambient color. And that's the reason why this is getting colorized as a brownish color. Because if I change this back over here to like a gray here, and then move this up, see quite a different result. You're just getting a lightening effect to it, and eventually will get overlit, if you will. And so here we're able to handle the overall fall off of the shadow on the surface here, and just how much light reflectance the surface gets basically with this ambient shadow value. And so we can use this as a controller. I'm wanting to show what each one of these parts here do first from a graphical standpoint, and then you have a better idea. Here, let me just turn up this ambient shadow value here a little bit more so you can see a stronger effect of the ambient color here. So now if I start changing, moving this around, you can start seeing how the ambient color is really affecting the shader and the surface of the model here. Okay, and then diffuse color. Diffuse color is our main color, and it's basically determining pretty much the color of the shader for the most part. Now, key important thing here, let me go ahead and pull this back down, and I'll turn this down to near black. I don't like doing totally black because it's unrealistic. Not even space is totally black, because you always have stars and some kind of light for that matter, so there's no such thing as total blackness. Because of that, I mean, the closest thing you have to total blackness is vacuum of space, but again, even then you still have starlight, so there's never truly total blackness in the world. But, you know, that's being artistic anyways. We can see we can change this diffuse value around. Okay, so let's start going over how you go about doing one of these shaders here. And I should have put in, alright, so up here you put the name of your shader and all this. I haven't done, I was lazy. All I did when I created the shaders, I went over here to Effect and created a new effect. And I named it, don't call yours Lambert Custom. I called it that. I should have called it LambertVertex. Please call yours LambertVertex. Because this is going to be the LambertVertex shader that we're doing here. Okay, so we're starting out with a float 4x4 world view projection colon world view projection semicolon for our variable here, and we're giving it the value linked to the actual OpenGL or DirectX of world view projection, and we're going to create a struct. I like structs. It just keeps things clean and easy, and that's wonderful. I really do. I love structs for keeping things very nice, clean, and manageable setup here. So struct here VS_IN, so VS for our vertex shader, and this is going to be the N value. All right, so we're passing this into the shader. And the two values we're going to pass in is going to be the position and normal. So key thing to note here is I got a float 3 here, and now these are curly braces here. If you have a hard time seeing that, these are curly braces. Let me see real quick. I don't believe they have a zoom on this thing. They sure don't, unfortunately. So there's no way I can actually zoom in on the interface here and show you, make it any bigger as far as I know. Unfortunately, I really wish there was, but it doesn't seem to be any way of doing that in this thing. So, as it is, I'll just kind of point out some stuff, and you can also check the code and follow along too. But these are curly braces here, rounding the structs anytime you have a struct here. I'm going to do a float 3 here, space position, with the uppercase P here. This is a colon, and then we're going to have position here, all caps, absolutely very important to be all caps. And then you're going to have a semicolon right here at the end to terminate that statement. Okay, so we have a float 3 here, a normal, a colon, and an uppercase, all uppercase, normal, semicolon, close curly brace, semicolon, to end that struct. And that just because we're going to be passing in our position and our normal for the surface. Now, if you remember back from previously, and let me just launch really quick. So is it in downloads? I believe it is, yeah. And I'll just hit up Blender 2.5a will work for me. And if you'll remember, I did a whole light model here earlier, and remember position is going to be your P or your point in your surface. We represent this as IP in the algorithm here. So here's our N. Now we're not concerned with this R and V right now. We're only concerned with N here and the L, and then P would be this point position right here that we're sampling from here. In this case, in the shader, we're talking about the position of the vertex. And we can simultaneously compute all these vertices with the different normals and light vectors simultaneously at the same time within these shaders here. So that's key to understand and know, because of the way the nature of a 3D card is parallel processing here. Okay, so we're going to go to the next part here. I'm just going to scroll on down to struct vs out here, and I'm going to open curly brace here, float 4, position, colon, position here, semicolon. So we're going to be going out with a position. This is a homogeneous coordinate position system here for a vector here. Float 4 color, colon, color. So RGBA, close curly brace, semicolon. Alright? And so the only thing we're really interested after we're done with all this is the color and position, and that's what we're outputting. We're not dealing with a pixel shader, so there's no pixel shader here, and we're dealing with strictly nothing more than color with just a vertex shader itself. So we've ditched the pixel shader altogether on this. Okay, so ambient light here, and we're going to set up a global ambient here. Now if you remember global ambient from your algorithm here, remember so IP equals KA and then I ambient. So I ambient would be your global ambient here. So don't forget about that. Something I forgot to show earlier was this web page here from Wikipedia. It's absolutely awesome. And they have the algorithm written out here with the eSum here. And typically you're going to have like, okay, so just because they didn't do it, typically you're going to have like N equals, or like in this case M equals 0, going up to, you know, number of lights up here, right, for the range. But basically everything else is pretty much as you expect. I named this one shininess because I thought it was more descriptive here. But I used a lot of the same naming conventions that they used for this algorithm. I changed some things around to make it easier to understand and follow on mine here. You know, like iAmbient, I think it's a little easier to understand, and some things like that. But for the most part, I kept it kind of close. Okay, so now you can see where those terms are coming from, where those different values are coming from there. So remember, iAmbient here is your global ambient one. All right, KA is going to be the ambient color property here, which I just showed off a second ago, and that does absolutely change the ambient color, as you can see it happening there. Remember, if I turn this up here on ambient shadow, it's going to have a stronger effect. Right now it's turned down quite a bit. Alright, and that's your KA. And remember, KA is going to be this one right here times your global ambient value there. And if you remember, that's also over here. So KA, IA, same thing. If you're getting confused, that's the same thing there. Okay, and I'm going to set these up appropriately here. So float 3 global ambient, and I did a couple G, couple A, colon ambient, and then nothing afterwards. Open, let's see here, that'd be what, less than sign. And then we'd have string space UI name here equals, in quotes, ambient space shadow, uppercase A, uppercase S, lowercase everything else, in quotes, semicolon here. and that's just because we're assigning this ambient shadow name basically to our UI interface. And it's important I say capital UI in and then lowercase AME for name. And we're telling it to be a string here. This is a special name here. So string UI widget, what kind of access are we going to do? We're going to do a color access here on this. That means when I click over here, it's going to give me a triple dot. It's going to give me access to this color picker. So it's important I tell it to be color here. Alright, so color inside of quotes, semicolon in that line. And this is UI widget with a capital UIW here, lowercase IDGET. And that equals there. And it's a string value. Then we're going to close with a greater than symbol here. And we're going to say equal and then open curly brace. This is not a parentheses, that's a curly brace. And then our default starting value here. In this case it's 0.07f, comma 0.07f, comma 0.07f. Close curly brace, semicolon. And that lets us set up our global ambient shadow here, as you can see, because you see this name here corresponds with the name here, and the color corresponds with the color picker. So don't forget about that. Okay, so the next one, I'm doing it as a constant, which means because if I'm doing it at a constant, then that's going to be what? That's going to be, oh, honestly, this should be a constant too. Because that's going to make it run faster for shader here. And that's important. Remember, you want to keep things constant as much as possible because that means it's going to be a uniform versus an attribute here in the shading, a varying variable, shall I say. And a varying variable uses up more resources than a uniform. So by me putting constant in front of there is going to make it run faster. So that's important. It's not something that you're going to have changing over a period of time on a regular basis here. So please be aware of that, as that matters. Okay. So, that way we know that the global ambient is not going to change per vertex across the shader. Instead, we're going to have a single value that's going to maintain the same value throughout the entire calculation of a single frame. So that's why it's got to be, that's why you can get away with it being constant there, because remember, we're setting up as a uniform, which uses less resources on the 3D card. Okay, so const here, space float 4, KA, and remember this is our user-defined artist control here for our ambient color. Our ambient color here, yes, alright. It's kind of like our fall of shadow value, and we can colorize it. Overall lighting color contribution, if you will. Okay, so we're going to do a const here, float 4, KA, colon, uppercase color all the way, and then a less than sign here, and then we're going to say string, and then we're going to say UI widget, or capital UIW, lowercase IDGET, equals, in quotes, color, and then semicolon. And then we're going to come down to the next line and do the same thing, string UI name, or it's capital UI in, lowercase AME, equals, in quotes, ambient color, semicolon. Now remember, color here is referring to the color widget picker, and ambient color is referring to the name here describing this variable, and this adds a UI interface to it for this annotation. Alright, and now we're going to do a closing greater than symbol, equals, and then curly brace. Don't forget, this is curly brace. And I give it a value of starting value of just a bright gray, if you will, 0.8f, comma 0.8f, comma 0.8f, comma 0.1f, closing curly brace semicolon. Now don't forget those F's matter, because why? F stands for floating point, and we're doing a floating point value here for our values that we're passing into OpenGL. So you need to denote those with F's. It's very important. It helps OpenGL. It is not an absolute requirement typically. However, it's best off to follow convention and to cause the least amount of problems possible. So just to help avoid problems, put F's there. Okay, next one. Let's do the KD. Now remember, KD is our diffused variable, artist controllable variable, and it's this one right here. And I'm going to just drive this around, and this is, remember, our main color, more or less, for the shader. And artists are familiar with what diffuse means. KD, they're not familiar with that. So if you put in a value of KD up here for the name of a variable, artist can be like, what on earth is that? You know, don't do that. Put in a name diffuse color here. So I've named it diffuse color. So here, hold on a second. We're going to do const float 4 space KD, capital K lowercase d colon color all caps here, and then we're going to have a greater than symbol, then string space capital UIW lowercase IDGET space equals in quotes color in quotes semicolon. And remember, this is for setting up our widget, so that it's going to be a color picker here for artist controllable interface device here in our annotation. Great. Then over here is where our naming convention here. So we're going to do string UI name, where it's capital UIN and lowercase AME equals in quotes diffuse color here in close quotes semicolon. And the diffuse color is going to be recognizable to the artist. And remember, you're going to call it diffuse color and not KD, even though it is a KD variable, because otherwise it's going to confuse the artist to no end, and they won't have a clue what KD means. It's usually best coming up with logical names that a human readable person would just be like common sense, know what it is. That's always the best thing to do, so the artist isn't scratching their head the whole time going, what on earth is this for? Sure, they can click around and figure it out eventually, but if you give good meaningful names to things, then artists can get up and going much faster, and that's what you always want to do. You never want to slow down production. They're always under such a terrible time crunch for the amount of work they have to pull out in such a ridiculous time frame typically on production. The last thing you want to do is slow them down in any way, shape, or form. And not to mention, your developments are typically going to be affecting multiple people. So you might be affecting 10 or more people with some of your stuff that you do. And if that's the case, you might be slowing down 10 people or something, and exponentially, again, cost is created because of poor development decisions here and there. So again, we want to keep our development decisions as clean and smart and straightforward as possible. Okay, so we're going to do a close greater than symbol here, and we're going to say equals, and then again it's going to be a open curly brace here, 0.8f here, comma 0.8f, 0.8f, comma between each one, 0.0f, close curly brace, semicolon. Again, curly brace and not parentheses. Now don't forget, the F's are important here, remember, because it means floating point for each one of these numbers. Okay, great. So that gets us set up with our KD diffuse. And if you remember now KD diffuse here was in our algorithm, and it's inside the eSum value here. If you need to see it from the web page standpoint here, here it is, KD being multiplied. And I did KD times ID here directly instead of moving it to the end. I don't like having it moved to the end like that. I like doing them in straight succession here, and then dotting my normalized vector of my normal here with my normalized light vector here. Okay, which of course points directly to the light. Okay, so now we have our value here for our KD here. Okay, great. Next thing that we need the lamp position, or shall we say the position of the light, and that's exactly what this does right here. So this is our point lamp 0, or point light 0 if you will, and we're going to say float 3 here, space lamp 0 pose here for the first light position, colon space position, capital P here, lowercase OSITION. Important that you write it just like that. Okay, open greater than symbol. And then, if you're wondering how I got to some of this stuff, by the way, real quick, Control J is going to bring up your interface here to where you can easily select what it is you want to make a link to with the interface here, and it's going to automatically fill in a basic default value setup here, and then you can, change it to your own needs and your own specific requirements. Okay. Just want to get that out of the way real quick. So yeah, again, greater than symbol here, then string, and then we have object here equals position point light 0, close quotes here, and then semicolon. And that's exactly what I have here. Is my point light here. It's my first light here. And the cool part about this, you may not have realized this already, but yes, I actually do have a light source interacting here with my Lambert shader. So we have broken away from just solid default lighting here without any actual shadow casting or capability now. Now we have real-time dynamic lighting happening in our scene, and this is when it starts to get pretty daggone cool. And that's why we're doing this, because real-time dynamic lighting is awesome to have in your scene. And that's essentially what we're doing right now. So we need to have our lights affect our surface in a real-time dynamic manner. Okay, so with that said, let's move on. So that's our point light position, and we have a close parentheses here, and not parentheses, but quotes, close quotes, I'm sorry, semicolon, and then string here, UI name here, and a capital UI and then lowercase AME equals, and then we have lamp 0 position. And so that lets us know that inside our shader, that is going to be lamp 0 position here, and it gets the position. Now the position is not something we define. You'll notice here, now when I click back here again, we get a totally different position in here. It's literally getting the position from the actual light, and it's being linked to that value. It's not an artist-driven variable, although they can see it in the interface here. So this is important. It's actually being tied directly into the actual light itself, and wherever the artist manipulates it or moves it, it's going to define the actual position of the light, and not something you change here in the shader. Yes, technically you could have a little pop-up here, and you could hand enter the values of the light, but that is so unbelievably frustrating and annoying. It is so much better and so much easier in order to just grab and move an object. Remember, when you're developing for artists, it needs to be hands-on, and you don't want to do standard programming. Go, oh well, yeah, it's so much easier to slap in this control here, where you just have someone enter in the value or numbers. But from an artist standpoint, that is absolutely insane, ridiculously difficult to position something, and it's going to be incredibly time-consuming, which is time they don't have. So what you want to do is make it as easily hands-on, directly tweak manageable in the viewport here as much as possible for artists, so that way they can really see what they're doing and easily and get things moving in position as they need them. The last thing you want to do is to slap a bunch of little controls to pretty much break the artist from their art environment, and that's what you're doing when you're having a bunch of hand enter in values. Like, you know, if I were to hand enter in this value exactly for the position on this thing, who on earth knows what, you know, the fine little position is going to be on a light or whatnot. So it's important to be able to have artist-driven control capability here. Okay, so with this, let's continue on here. And here we have our string, and our space is equal to world. So we're having it set to a world space coordinate system versus local coordinate system. So it's being driven as a world space coordinate position here, and a string with the uppercase S for our space here, and then PACE lowercase equals world in quotes semicolon. And then we're going to end this up with a less than sign here, and then equals with an open curly brace here, equals, sorry, not equals, open curly brace here, and then negative 0.5f comma 2.0f comma 1.25f close curly brace semicolon. Awesome. Alright, so next let's look at the actual color from the light, and how the light intensity could, you know, best way to call it really. In this case it's lamp color here, or light color if you will. That's a great name for artists. They can follow along with that easily, so that's really nice to call it that. And essentially, basically, whatever the color of the light is, we're getting the actual light color from the actual light itself, and we're not defining it so much as we are getting it, okay? So with this I'm going to say float 3 here, space lamp 0 color, colon, space specular, then open greater than sign here. I'm sorry, there'd be less than sign here. So opening less than sign here, and then we're going to go string here, and then space capital UIN, and then lowercase AME space equals space in quotes. Here we're going to have lamp 0 color in quotes semicolon here, and that defines the name for it. And if I click back over here again, we're going to see lamp 0 color here, referring to our first light here, and it's seeing the light color that's assigned to this. Now you can have as many lights as you want with this, but you would have to create connections to those, so that way you can assign lights to the shader. But that's one of the benefits of this. You can actually have as many lights as you want. Since we've broken free of the fixed function pipeline, we are no longer confined to just 8 lights in a scene. Because we're doing our shader programming here, we can have as many lights as we want, and this is how you get into multi real-time lighting scenario beyond 8 lights. If you're trying to do something like that, this is how you do it in the next gen and current gen platform development. Okay, so, and that's key important aspect of this. Alright, so we have string space object with a capital O here and the lowercase bject equals, in quotes here, point light 0 close quotes semicolon, and that's pointing to our light. So that's important. We need to specify what light object we're talking about here. String UI widget equals, in quotes here, color, and then semicolon. So we're saying what? We're saying it's going to be tied into the actual color attribute here. Open greater than sign here, closing greater than sign here equals, in opening curly brace 1.0f, comma 1.0f, comma 1.0f, close curly brace, semicolon. Now remember, it's just going to be RGB. There's no A, there's no alpha when you're talking about light color. It's not even feasible. So of course, that affects it. But check it out. I can go in here and change my light color, and it's actually affecting my shader. Now my actual shader is what? It's gray. But because my light is a certain color, it's actually colorizing my shader. Now that doesn't mean I can't go in here and have one light for my diffuse here. Like for instance, say I do blue, okay? Alright, that's pretty blue. And I come in here to my light and then do a colored light. You can see an effect of that. So yes, we do actually have color light scenarios here. And that's a highly saturated blue at that. Probably be an easier time showing that off if I desaturate that color some more there. Yeah. And so we have the effect of color light upon the surface. And I could have multiple color lights here and driving it and all this stuff, but anyways, we're just going to stick with one for now. And I don't know, we'll just colorize it. Oh, how about blue like that? That blue doesn't look too bad. We'll stick with the blue for now. Alright, so moving on. Alright, so we're going to have our vertex shader here. And this is our VS out. It's our return type. And remember, VS out is from our struct here. Our struct is VS out. Like so. And so that's what we're saying as our return type. And what we're going to be passing in is our VS in. And this is the struct that we're passing in. So we're passing in our position and our normal, and then we're going to be returning our position and our color from our main function here. So VS out is our return time. Main VS is our name of our main function here for our vertex shader here. And that's what the VS stands for, is vertex shader. And then in parentheses here, I have VS in space in here. So I'm passing in this value, and the in value here is going to be what? It's going to be struct in. So now our variable is called in. So every time we have our in variable is basically from the struct data type. Alright, so VS out here for vertex shader, and we call it variable named out in all caps here, semicolon. So now we know everything is going to be going out and all the stuff coming in. So float 3p here, remember P is point on the surface here. This is the point on the surface. If you look over here at Blender, this point here where we have our normal and our light vector here pointing to our light is all coming from this point position here. And that's what our P is, okay? So P, if you want to think of it as IP from the algorithm here, IP here, or if you want to think of it from, IP here in this algorithm. Alright? That's key. Alright, and then in is our normal here. And sorry, P equals in dot position semicolon. So this is our point on our surface, or our vertex, if you will, for this particular computation on this particular vertex. And this is going to happen for all the vertices on the model, of course. Float 3 here, in, and then equals in dot normal semicolon. So this is the normal vector that we have here. Now if you remember right, over here is our in, and this in is our normal vector in our light model shader for our Lambert shader. Awesome. And then we're going to pop back over here, and if we look at it real quick, here's our in value here in this algorithm, and then here's the in value in this one here. And we're dotting this with the L vector here, or our light vector that we're aiming towards, okay? Alright, so let's go back here real quick, and let's have a look at that. Alright, so that's our in normal. And then we have our ambient. Remember that how we did our ambient here. We're saying ka.rgb times our global ambient.rgb. Now if we looked over here, remember we can calculate ambient as ka times I ambient. And that's exactly what we've done. We've done our global ambient here value, which is our ambient shadow, times our ka ambient color, okay? and that gives it our overall ambient value, and we're just assigned it as the ambient color there. Awesome. Alright, next we have our float 3L. Remember, L is pointing to our light vector here, so it's going towards our light here, and hopefully this is making sense as I keep hitting this over and over and over again. I know hopefully it's not too boring, but at the same point I want you to have this down and understand where this is coming from. So here we have from our point here for our vector all the way to our light here for our vector, and that's exactly what we're referencing. If you want to look at it from over here, that would be our LM in this algorithm, or it would be considered our LM in this algorithm here, showing it. And this is for calculating our dot product here for our going along with our KD term here for our diffuse. So here we have our L. Alright, so we're going to normalize it. So we're taking our lamp position minus our P, or our point position. So what we're doing is we're finding the difference between the, or shall we say distance, if you will, between our and direction. And when we normalize it, we just get the direction. So we don't end up with the distance, which would be the magnitude. We just end up with the direction in which it's facing for the lamp light position. And that's key important thing. So that way, when we're moving, this is why it matters. So when we're moving the light around, it knows how to do the shine highlight on the surface from the light position, and how to do the shadow and light aspects of this. If you don't do that, then it wouldn't know which way the light would be facing according to the surface to be lighting the surface. So that's why we have to have this vector position here. Otherwise, there's no way the computer would know, how to calculate the light on the surface for shadow and light intensity. Okay, so that's why the L vector matters so much. Okay, so that gets normalized. So again, this is our lamp position, or our position of our light, subtracted from the position of the point, say point on the surface, and that gives us the direction once we normalize it, and that gets assigned as L. So that'd be your X, Y, Z axis here for our values. Okay, then float diffuse light equals, and here's our diffuse light, and our diffuse light is max here dot our N and our L. Remember, we have to do the dot product of our normal vector and our light vector, and going from here to 0 on that. So that's very useful. And then we're going to do our float 3 here, and we're going to say diffuse, and so we got our range here. So the maximum is this value, and then to 0 for your minimum. Alright, so we have float 3 here, diffuse equals KD.RGB. Alright, so remember KD is our diffuse value here. So if I click on this right here, this is our diffuse color. Remember, KD is our diffuse color. Okay, don't forget that. Alright. And if you want to see what the KD is from a mathematics standpoint, it's this one right here. That we multiply times our ID. And that's also the same thing over here too. So here's our KD right here. Very cool. Very cool indeed. So there's our KD. And so KD.RGB times lamp color.RGB. Now remember, our lamp color is our color of our light. So that gets into our light value. Now that might be confusing, but let me point this out. ID. There's your light color. ID. Awesome. Same thing over here. It'll be I lowercase d here. I prefer uppercase I for that stuff, but anyhow, that works fine, and that's what your ID is right there. So it's our color of our light, if you will. Okay, and then times our diffuse light. Now our diffuse light, remember, is what? It is the dot product of our N and L, already normalized for our normal and our light vector. Awesome. Light position vector, shall I say, to be more accurate. Okay, so out.color equals float 4, and then open parentheses, ambient dot XYZ, alright, and then plus diffuse dot XYZ, and then close parentheses dot XYZ on this. So after these get added together, it ends up being an XYZ overall value. And then we add 1 to this overall as a float 4, so that we have what? RGBA. So our ambient and our diffuse are only RGB, and I have this as XYZ, but I could actually change this over. RGB. That'd be better if I did that. RGB. Since we're talking about color, it's best if I just name this accordingly. And then position, I'll stick with XYZ. Rebuild, and everything works perfectly fine. I can do that, that's no problem. Okay. So with that, let's keep it as RGB instead of, since we're dealing with color here. Either way it'll work, but better off keeping, just for ease of use and following what is going on, it's best to use the best naming conventions, and RGB makes more sense than XYZ. I do see other people do that too. They use XYZ in place of RGB for things, but it's really not good to do that. It's really good to keep this standard here on our naming so that it's easy to follow. Okay, so ambient.rgb plus diffuse.rgb. And then remember, we calculate our diffuse over here, and we calculate our ambient over here. So we're adding these two values together as a .rgb and then 1.0, and this is all getting past the color. Great, so now we have our color out, and we're almost done. Now we're down to our out.position, and of course there's a semicolon. And these are all parentheses, of course, for each one of these parts here. Okay, so out.position equals mul for multiply, open parentheses here, and then worldview proj, comma, float for open parentheses in.position.xyz, comma 1.0, close parentheses, semicolon. So what we're doing, we're multiplying our worldview projection matrix times our positions of each vertex here in the homogeneous coordinate system here. Alright, so it gives us our position of each vertex and it gives us our color with the model view matrix manipulation. Technique 0 here, setting up, close curly brace here, and we're going to return out dot semicolon, of course. Alright, but yeah, we have our closed curly brace here to end the statement. Alright, so we're going to have a technique here, and then it's technique 0, open curly brace, and then we're going to say pass space P0 here, and then open another curly brace, and then we're going to do our depth test enabled, and that's capital D, capital T, capital E, everything else lowercase, equals lowercase true, semicolon. That's important. Depth mask here is capital D, capital M, lowercase all the other letters here, equals true, semicolon. Coal face enabled is capital C, capital F, capital E, lowercase all the other letters in here, equals false, semicolon. And you need to spell it exactly as it's written here. If you spell it, misspell it, it will not work. Blend enabled, we're going to do capital B, capital E, lowercase everything else, equals false here, all lowercase, of course, semicolon. And then we're going to do one more thing here, and that's our depth func here. And our depth func is capital D, capital F, and equals capital L-E, important, lowercase, rest of the letters here for equal, which is Q-U-A-L, semicolon. That's L equal for less than or equal to. Don't forget, L equal means less than or equal to. And then a space here, and we're going to do vertex program, capital V, capital P, equals compile VP40 space main VS, open close parentheses, semicolon, then close curly brace, close curly brace. We're doing this close curly brace here because it matches up with our past. Now you notice something, if I put my cursor around any of these particular ones, it does the matching set of closing curly braces here, so that's important. And this curly brace is tied with this curly brace here. So key thing here, we have to have our closing ones to go with that. Alright, and I believe we have to have VP40 and not VP30 for our... Okay, no, it works. We can get away with that. Can we get away with 20? Probably not. Wow. Make sure I have the right... I do have the right one. It's wow, we can go all the way down to VP. I don't think there is a VP10. If I remember right, there isn't. Yeah, there's not one. It's the ARB one. Very cool. Amazingly, you can go all the way down to VP20 on this one. Nice. That's really great. So you can go pretty old on on this particular technique as far as implementing lights and shadow with well, not lights and not casted shadows, but just shadows within the LM as far as that goes. Well, not LM, but the vertex shader as far as that goes. We can go to at least VP20, if not lower, maybe even lower. I don't know. But very nice. And again, we're using our main VS here because that's tying back to our main VS function for our, and then main stands for our main vertex shader here, and that's why I call it main VS here. Open close parentheses, as we don't pass anything into here, semicolon, and it's all handled perfectly fine. That's it. for doing our vertex shader. That's going to be our overall shading for Lambert. Now, don't forget, we added these together, and that ties back into our values over here. So if you look at it, we have, where you have your shader color, and you would add emissive plus ambient plus diffuse plus specular. In this case, we're only working with a Lambert shader with no glow, so we only have ambient and diffuse, and we don't have specular and emissive, and that's why we left those out. But remember, this is kind of like the pseudocode, if you will, where it just covers basic ground rules of what we need to add together, and how we actually implement it into the shader is going to be a whole nother ball game. But this is the actual code in CG here, but it gives you a really good idea of what it is that needs to be done. Alright, so with this, that covers Lambert shading for vertex shading only for light model of Lambert light model, and we haven't gotten into how to add texture to this. Okay, in the next part here, we're doing this texture-based Lambert vertex shader, which means we used very little of an actual fragment shader in order to accomplish this. But first and foremost, you're going to need to go in and make a copy. Copy all the code here, select all the code, Control-C the copy, C as in cat, and you're going to go here to create a new effect, and then name it like Lambert Texture VS, for instance, like this. Okay, so with that said, let's look at what we need to add to the shader. So we have the exact same thing, and the only thing we're going to add here is a very small number of type of objects that we need. In this case, we're going to need float 2 because we're going to have only two float values here, U and V. So float 2 here for the UV, colon, texture chord 0, semicolon. We need to add that into our VS in. And for our VS out, same thing. You can copy and paste it right in here and get float 2 UV, colon, text chord 0, semicolon. And remember, that's a float 2. Okay? And then we're going to have FS out, or you could do a PS out, I don't care. FS for fragment shader, PS for pixel shader out. Either way. And the only thing we're outputting here is going to be color. So it's going to be a float 4 color, and it's colon, color, semicolon. And of course we have open, close curly braces with a semicolon here, and instruct here, FS with a capital O for out. Alright. And that covers a lot of that. Now everything else remains the same, except for when we get down here to this one part, and that's going to be our color and texture. And you'll remember this from before, from when we did some of the texture videos from before. But I basically broke out a set of comments here for color and texture, so I can define that section. And then I'm doing a texture here, so I'm going to define my texture, and then I'm going to apply that texture to my color sampler, so don't forget about that. Texture is a special keyword to let us denote a particular texture. So here I'm going to call this one color texture as a named variable in order to point to my texture. And then I'm going to do an open, and I'm going to do this for better conventions here, open less than sign here, string, and then resource name, capital R, capital N, everything else lowercase, equals, in quotes, default underscore color dot DDS, close quotes, semicolon. Now this is in the default folder for texture, so it's this one right here. And it'll automatically be able to find it and pull it up, no problem. But end it with a semicolon, then go down the string and say UI name equals, and then in quotes we're going to say diffuse texture, so that we know this is the diffuse texture, semicolon. And then we're going to say string resource type equals 2D, in quotes, a semicolon here, and that resource type is going to be capital R and T, lowercase everything else. Close greater than sign, and then do a semicolon at the end for our annotation. And that sets up our texture annotation. Now we need to apply this texture to our color sampler so that it can be accessed per pixel or per fragment, as you want to call it. Okay, sampler 2D, and this sets up a sampler 2D for our color sampler. Alright, and we're going to say color sampler for the name of it, and this is equal to sampler underscore state, all lowercase, and then open curly brace, keyword, open curly brace. Alright. Texture equals open less than sign color texture with a capital C and a T, close greater than symbol, semicolon. Then we have our min filter, minimum filter here. So min filter with a capital M, capital F, lowercase everything else, equals linear mip map linear, semicolon, with capital L M M L here. Everything else is lowercase. So linear mip map linear, semicolon. That is not a typo, that is the way it's written. Mag filter, or as you would refer to it as like a max filter. The mag filter here is our maximum filter. So it is mag. It is not a typo. That is what it is. So it's mag filter equals linear semicolon. That's capital M and F there. Everything else lowercase. Wrap S here. So we're going to do capital W S here. Everything else is lowercase. Wrap S. Remember, we're renaming our U and V as S and T in order to recalculate our UVs, because you cannot directly manipulate the UVs. You can only manipulate it through mathematics on like a S and T, and again, this is going to be standard, otherwise you are going to screw it up for everyone else, because everyone in the industry uses S and T. So wrap S equals repeat semicolon, wrap T here equals repeat semicolon, capital R for repeat, and that's wrap T, and these are special names. So make sure you use exactly what is written here, as that capital W and a capital T, lowercase everything else. Okay, closing curly brace semicolon. Alright, and so that covers texture. Awesome. Now there's only one other thing here we need to have a look at, really, and there's really not that much difference between the two. You have the exact same thing throughout this whole part right here as the previously, until we get down here to our out UV. So we need to say out.uv equals in.uv. So we need to pass our UVs out, and then we're going to return our out as normal. So again, that's out.uv equals in.uv semicolon. Okay, and then we're going to add our PS main shader that we didn't have before. And this is going to be our FS out, and we're going to have our main PS here, or you can call it FS, I don't care. Open parentheses, VS out, and then IN. So what was our outputted vertex struct here is going to become our input to our pixel shader. So what we pass out of our vertex shader goes into our pixel shader as normal, or fragment shader, however you want to refer to it. FS out, and then we have struct here and an out. Remember, all that contains is color. That's the only thing in that struct, semicolon. So we have out.color here, and then we're saying equals in.color times text 2D open parentheses color sampler, capital C, capital S, lowercase everything else, comma in caps dot UV in caps close parentheses semicolon. Remember, this is curly braces here. These are not semicolons. And then we're going to say return out semicolon, and that is going to be returning our variable here, our value of color out there per pixel. Alright, and this allows us to have a texture applied to our surface. Very cool. And it certainly helps. So in this case, we're just taking our final result of our shading here and then multiplying it times the color in order to give it a color for our texture, for our diffuse channel. And since we only have a very simple setup on our shader, we're not having to worry about specular values with texturing them yet, because we're only dealing with a vertex shader. It doesn't really matter right now. Let's see here, which one is our particular vertex shader material? That's looking like it right there. So if I apply that, there it is. So I don't have that specular value. Sorry, I had the fall shader applied a second ago there. So I was just messing with that. So get rid of that highlight value, and we have just our Lambert with our texture applied. That's pretty much it. The only thing else we have to add to this whole thing is down here in our fragment shader, right here. So our fragment program here equals compile FP40 space main PS open parentheses close parentheses semicolon. That's a capital PS there, and that's it. And that will execute and work fine. And don't forget, again, these are closing curly braces. All right. So moving on. All right. So with that, that covers vertex shader Lambert's light model. My name is Nate Nestler, and this is for Hyperactive Studios. Thank you very much.